Welcome back. Today we will discuss traffic measurement and a mathematical model for traffic. So with respect to traffic measurement, it is very important for an operating company to know how much busy hours traffic its systems are handling. Not only that, it needs to know when the systems are becoming overload and whether additional equipments are required to be installed or not in the particular area. Thus, the traffic should be measured regularly and records must be kept. Since equipment must be manufactured, installed and commissioned before it enters service, it is always preferred to know the traffic forecast of a future date. It is always very important to know what will be the traffic in future coming days before the service is commissioned. So it is clear that measuring the traffic means counting the number of calls that are in progress at regular intervals. We need to consider or we need to count the number of calls that are in progress at regular intervals during the busy hours. Of course, we will be dealing with busy hours and later we will average the results. So in the early days, engineers used to count the plugs that are inserted in a manual switchboard in a manual exchange. So depending upon the number of plugs that are inserted in a switchboard, they used to find so many number of calls that are in progress. Whereas in an automatic exchange, the number of selectors that are off normal are counted. So the results that are obtained with respect to manual exchange are said as peg count, whereas with respect to automatic exchange are said as switch count. This defines the number of calls that are in progress at a particular instant. Since this method was laborious, automatic traffic recorders were developed and installed in automatic exchanges. Since this manual exchange as well as automatic exchange, that is with respect to selectors of normal calculation or number of calculations, are somewhat laborious, so automatic traffic recorders were developed and installed inside an automatic exchange. In modern stored program exchange system, the central processor generates records of the calls that they set up. So stored program control exchange is a advanced exchange. It is also called as SPC exchange. So it will be having a processor which will keeps a track of number of calls that are set up or number of calls that are in progress. So which defines the traffic or which measures the traffic in a system. So let us solve an example in which it is observed that the number of busy lines in a group of junctions at intervals of 5 minutes during the busy hour. So the results obtained were 11, 13, 8, 10, 14, 12, 7, 9, 15, 17, 16 and 12. So we need to find the traffic carried by the system. So inside this 5 minutes of duration, that is with 5 minutes duration, after 5 minutes we have recorded some traffic or number of calls or the busy lines. Then after 5 minutes we have recorded this. So like this, inside a busy hour we have recorded these are the number of lines that are busy. So we need to find the traffic carried by the system inside that particular busy hour. So the traffic carried by the system, of course, that is expressed in Erlang, is computed as the average of those values and that is obtained as 12. So please note that even though at particular instant we are offering 17 number of calls that are in progress, but once we take with respect to a particular busy hour, so it was obtained as per Erlang. So this mathematical model gives the required analytical solution for the given telecommunication system. So a simple mathematical model is based on the following assumptions. So these two assumptions must be satisfied by a telecommunication system to give required analytical solutions in the form of a mathematical model for traffic. So these two assumptions are pure chance traffic as well as statistical equilibrium. So with respect to pure chance traffic, the assumption of pure chance traffic means that call arrivals and call terminations are independent random events. So here call arrival and call terminations are considered as random events. So the total traffic generated by a large number of users is observed to behave as if calls were generated at random. So it is clear that the total traffic that is generated is because of large number of users. So this pure chance traffic assumes large number of users are involved in generating this total traffic, and of course calls arrivals or calls are generated at random. As defined, call arrivals are independent random events. Their occurrence is not affected by previous calls. Hence we can say this traffic as a memoryless traffic. So this assumption of random call arrivals and termination leads to the following results. So basically we are dealing with three different results. The first result is the number of call arrivals in a given time satisfies Poisson distribution. So the number of call arrivals already considered, it is a random event and that is going to satisfy Poisson distribution. Accordingly we can write probability of x number of calls that are in progress to be equal to mu power x by x factorial e power minus mu, where x is the number of call arrivals in time t and mu is the mean number of call arrivals in time t. So the difference between x and mu will be calculated. We will come to know the difference between x and mu when we solve one problem. So generally x is the number of calls that are in progress and mu is the mean number of calls arriving in time t. Of course calls that are in progress, or I can say x is the number of call arrivals within that particular time duration t. So for this reason pure chance traffic is also called as Poissonian traffic. Since this pure chance traffic is satisfying Poisson distribution, sometimes we call pure chance traffic as Poisson traffic. So we will come to second result, in which the intervals t between call arrivals. So we will be dealing with time interval between two call arrivals. So the interval t between call arrivals are the intervals between two independent random events, and it is shown that these intervals have a negative exponential distribution. Accordingly we can write p of t greater than or equal to t equal to e power minus t by t bar, where t bar is the mean interval between call arrivals and t is the interval between two successive events. We will come to know difference between t bar and t when we solve one example. So probability of having time t between two calls can be written as e power minus t by t bar. Of course t bar will be given, the mean interval between call arrivals will be given in the question. So the next result is the arrival of each call and its termination are independent random events. So the call duration. So previously we were dealing with duration between two calls, but now inside a single call, the call arrival and call termination, the duration is called as call duration, or sometimes we call it as holding time. Call duration capital T. This is also the interval between two random events. So we are considering call termination as well as call arrival as random events. Between these two random events, we are going to satisfy, or it is going to satisfy, negative exponential distribution. Accordingly, we can write P of t greater than or equal to t equal to e power minus t by h, where h is the mean call duration, or also called as holding time. H is the mean call duration, and this t is the call duration between call arrival and call termination. So next, let us deal with statistical equilibrium. So this is the second assumption of our mathematical model. So with respect to statistical equilibrium, so here also the assumption of statistical equilibrium means that the generation of traffic is a stationary random process. It is a stationary random process, that is, probability do not change during the period being considered. So it means that the generation of traffic is a stationary random process, and also the probabilities are not going to change during the period being considered. Probability of occurrence will be same as that of probability of ending. Like that, we will assume the probabilities are not going to change during this particular interval or during that particular period. Consequently, the mean number of calls in progress remain constant. So previously we have discussed figure B, which shows that this condition is satisfied, that is, statistical equilibrium condition is satisfied during the busy hour, and it is of course the busy hour grade of service we are much more wishing to determine. So the statistical equilibrium is not obtained immediately before and after the busy hour. So this is one important thing you should remember. Statistical equilibrium holds good during busy hour only. So let us go to figure B as defined previously. So the traffic more or less will be constant within this busy hour. So we will assume according to statistical equilibrium, so the probability of occurrence as well as probability of termination of a call is almost remains same. Of course, before this busy hour as well as after this busy hour, statistical equilibrium is not going to satisfy. Only during this busy hour, statistical equilibrium will be satisfied. So let us solve an example where they have given on an average one call arrives every 5 seconds. During the period of 10 seconds, what is the probability that no call arrives? One call arrives, two call arrives, and more than two call arrives. So they have directly given that one call is arriving every 5 seconds. But we need to compute all these things with respect to 10 seconds. So first we need to calculate what is the value of mu. So as previously defined, mu is the average number of calls that are arriving. Since they have given 5 within 5 seconds one call is arriving, so mu becomes 10 by 5, which is equal to 2. So coming to our standard equation, P of x, probability of x number of call that are arriving, P of x is equal to mu power x by x factorial e power minus mu. So accordingly, first we need to calculate with respect to no call arrives. So within this 10 seconds, no calls are arriving. So probability of 0 is equal to 2 power 0 by 0 factorial into e power minus 2. So 0 factorial is 1, we know that. So this becomes 2 power 0 is 1. So e power minus 2, which is equal to 0.135. Similarly, we will calculate one call arrivals. So P of 1 is equal to 2 power 1 by 1 factorial e power minus 2, and this was obtained to be 2 into e power minus 2, and it is equal to 0.27. Similarly, 2 call arrivals within this 10 seconds. P of 2 is equal to 2 power 2 by 2 factor e power minus 2. So this is written according to this equation, and this was found to be 0.27. Similarly, more than 2 call arrivals can be computed as P of greater than 2 equal to 1 minus all these three summations: probability of having 0 calls, probability of arriving 1 call, probability of arriving 2 calls. So that gives probability of having calls greater than 2, and it was found to be 0.325. So please note that this equation or this example is based on our first result of pure chance traffic. So this is what our first result of pure chance traffic. Similarly, let us discuss with respect to second result. An example with respect to second result. Let us consider in a telephone system the average call duration is given to be 2 minutes. A call has already lasted 4 minutes. What is the probability that the call will last at least another 4 minutes? So the call will end within the next 4 minutes. So they are saying that the average call duration is 2 minutes, which is H. H is given, average call duration, or which is nothing but holding time is generally it is about 2 minutes. But right now a call is already in progress and it has already lasted 4 minutes, and they are asking us to calculate what will be the probability that it will last for another 4 minutes. Similarly, what is the probability that it will end within the next 4 minutes? We need to compute. So please note that the probabilities can be assumed to be independent of the time which has already elapsed. Already we said pure chance traffic or traffic as a memoryless traffic. It means that so whatever the call it has already lasted is completely independent on what will be the next duration it lasts. Similarly, how long it will end, within what duration it will end. So all those things are independent on what is the number or what is the duration it has already lost. So this data is not relevant, or this data is not required at all for calculation of these two components. So first let us calculate the probability of call duration greater than or equal to 4 minutes, that is P of t greater than or equal to t is equal to e power minus t by h, and right now they have given t as 4 minutes, and we know average holding time or average call duration is 2 minutes, and this was found to be equal to e power minus 4 by 2, and it is e power minus 2, and this will be equal to 0.135. Similarly, we can calculate P of t less than or equal to 4, and that is equal to 1 minus P of t greater than or equal to t, and this will be equal to 1 minus 0.135, and it was found to be 0.865. So by this it is clear that the call will end within the next 4 minutes, and the probability of ending the call within next 4 minutes is 0.865. So with this understanding, that is pure chance traffic and statistical equilibrium, let us go for designing a mathematical model for traffic. So we know for a group of n trunks, the number of calls in progress varies randomly. So as shown in figure 1, so as shown in this figure A, so the calls that are in progress are going to vary randomly. We know that with respect to time. So the number of calls in progress is always between 0 to n. Since there are n number of trunks, we can accommodate n number of calls. Of course, we can accommodate zero number of calls also. If no calls are there, you can consider it as 0. So it thus has total of n plus 1 different states. So including 0, we will be having n plus 1 different states, and this behavior depends on the probability of change from each state to one above and to the one below it. Such a process is called simple Markov chain. So a total of n plus 1 states are there, and the state transition probabilities increases by 1 and it may decrease by 1 as explained by Markov chain. So this is what state transition diagram for n different trunks. So here total of n trunks are there and total of n plus 1 different states are involved. So total n plus 1 states are involved here with respect to state transition diagram. State 0 indicates probability of having 0 number of calls. This indicates probability of having 1, probability of j number of calls, probability of k number of calls, like this. So P of j is the probability of state j. Similarly, P of k is the probability of the next higher state, that is k. So we can have P of j comma k as the probability of state increase to k from j. So as shown, so P of j comma k is the probability of state transition from j to k. Similarly, P of k comma j can be said as probability of state transition from k to j. So k to j transition takes place if one call is terminated. If one call is terminated, it decreases. Similarly, if call arrives, it will increase to next state. So the probabilities P of 0, P of 1 up to P of n are called state probabilities, and the conditional probabilities P of j comma k, P of k comma j are called this transition probabilities of the Markov chain. If there is statistical equilibrium, these properties do not change and the process is said to be regular Markov chain. So basically we are dealing with a mathematical model for traffic, that is by assuming it satisfies statistical equilibrium. So within this statistical equilibrium, so we will assume, or according to statistical equilibrium, all probabilities are not going to change. Almost all they remain same. So such scenario is said as regular Markov chain. So now let us consider a very small time duration of time delta t starting at time t. Since delta t is very small, the probability of something happening during this time delta t is almost neglected, is very small. So the probability of 2 or more events during delta t is therefore negligible. So since delta t is very small, so we will assume no 2 or more events are going to occur within this delta time. Of course, one event is acceptable. So the events which can happen during delta t are those as follows. So within this time duration delta t, we may have one call arriving with a probability of occurrence or probability of arrival P of E. Similarly, within this delta t, we may have one call ending with a probability P of E. Probability of ending a call is defined as P of E. Similarly, there may be no change with probability 1 minus P of E minus P of E. So as we know, the traffic carried by a system is given as A equals CH by T. So by this equation, it is clearly known for us the mean number of call arriving during the average holding time H. If I make this T as H, then the number of calls arriving becomes equal to traffic carried by the system. So C is going to become equal to A. C is going to become equal to A if I make the time duration that I am considering to be exactly equal to that of average holding time H. So thus the mean number arriving during time delta t is, or the mean number of calls that are arriving during the small duration delta t can be defined as A times delta t by H. So please note that. So what I am saying is, I want to know within this small duration delta t what will be the number of call arriving. So or we can call this as mean number of call arriving during this delta t. So this term will be equal to A times t. Right now we are dealing with delta t time duration. So A times delta t divided by H. So this H comes to LHS, becomes A delta t by H. So this becomes the number of calls that are arriving within this small duration delta t. Is it clear? So since delta t is very small, A times delta t by H is assumed or will be obtained as very smaller compared to 1. So this value is very smaller than 1. And this represents the probability of occurrence or probability of call arrival, P of A of a call arriving within this time duration delta t. So probability of call arrival is nothing but P of j comma k. So as we have seen in this state transition diagram, P of j comma k is nothing but probability of call arrival. So once call arrives, state changes from j to k. Similarly, once call terminates, it changes from k to j. The probability P of k comma j, we call this as probability of ending, probability of call ending P of E, whereas this is probability of call arrival P of A. So if the mean holding time is H and the number of calls in progress is K, so one can expect that an average of K calls can end during a period H. So as I said, probability of call arrival or number of call arrivals, once I make this T as H, will be equal to A. Similarly, already let us say some K number of calls are there. So when I make this T to H, so K number of calls may end. Within this average holding time. So when I make this T to H, the number of calls ending may become equal to K. So accordingly, the average number of calls ending during delta t can be defined as K times delta t by H. K times average number of call ending during this small duration delta t can be defined as K times delta t by H. Since delta t is very small, so this entire time will be very small than 1. And this represents the probability of ending. So please note that any probability cannot be greater than 1. Probability of ending of a call within this small duration delta t can be defined as P of k to j equal to P of E, which is K times delta t by H. If the probability of j calls in progress at time t is P of j, then the probability of a transition from j to k busy trunks during delta t will be written as P of j to k. So transition from j to k will be equal to probability of j times probability of occurrence P of A. So probability of transition from j to k can be defined as probability of j into probability of call occurrence, P of A, and we know P of A is A times delta T by H, and let us call this as equation number 6. Similarly, if the probability of K calls at time T is P of K, then the probability of a transition from K to J busy trunks during delta T will be equal to P of K to J, that is equal to P of K into P of E. This will be equal to P of K into K times delta T by H. So we know that according to statistical equilibrium, probabilities are not going to change. So P of J to K will be exactly equal to that of P of K to J. Otherwise, if they are not equal, so the number of calls that are in progress within this busy hour may steadily increase or decrease. But that is not occurring. Inside busy hour, the probability of call arrivals is almost same as that of probability of call ending. So that is about statistical equilibrium. So if this condition is satisfied, so then we can equate 6 and 7 since these are same. So accordingly, from equation 6 and 7 we can write K times P of K delta T by H equal to A times P of J delta T by H. So I have taken K outside. Here K is taken outside. So since delta T by H cancels each other, probability of having K number of calls will be equal to A by K to P of J. Let us call this equation. This is a very important equation. So based on this equation, let us have the number of calls that are in progress. P of 1 can be written as A by K, which is 1, to P of 0. Since we know the relation between K and J. If this K is becoming 1, of course J should be equal to 0. Similarly, we have written an equation for P of 1 as A times P of 0. Similarly, we can calculate P of 2 equal to A by 2 by P of J. A by 2 into P of 1. Sorry, P of 1. P of J here, J is 1. This will be equal to, if I substitute what P of 1 is, so I can have P of 2 to be A square by 2 into 1 into P of 0. Instead of writing 2, I can write 2 into 1. Similarly, probability of having P of 3 will be A by 3 into P of 2. If I substitute this, I end up with this equation. Or in general, I can write the number of calls that are in progress, P of X, as offered traffic 8 power X by X factorial into P of 0. So let us call this as equation 9. So now what we do is we will have an equation for P of 0. We will have an equation for P of 0. So because this need to be calculated. So the assumption of pure chance traffic implies a very large number of sources are involved. So as I said before, with respect to pure chance traffic, the total traffic is generated by a large number of sources, a large number of users. So thus X can have any value between 0 and infinity, and the sum of their probabilities must be unity. So probability of having X number of calls or probability of having any number of calls, if I summation all of those, I should end up with value 1. So 1 should be equal to summation X varying from 0 to infinity P of X. And if I substitute what P of X is from equation 9, then I will end up with summation X varying from 0 to infinity A power X by X factor into P of 0. So this term is going to be E power A. So with increase in traffic, exponentially this value increases. So for this term we can write it as E power A into P of 0. So we know 1 is equal to E power A into P of 0. So by this I can write equation for P of 0 to be E power minus A. P of 0 can be written as E power minus A. If I take this E power A to LHS, then it becomes 1 by E power A, which is nothing but E power minus A. And if I substitute P of 0 as E power minus A in this equation, then equation 9 becomes probability of x equal to a power x by x factor into e power minus e. This is a very important relation. It's a very important relation defining what is the probability of having x number of calls provided a is the traffic carried by the system. Of course, we have eliminated p of 0 here itself. E power minus e. So thus if call arrivals have a Poisson distribution, the number of calls that are in progress, of course the number of calls in progress as well as call arrivals are going to satisfy Poisson distribution. So this requires an infinite number of trunks to carry the calls. So to derive this equation, we have assumed that infinite number of calls are possible. So of course, by making use of Poisson distribution, we have arrived this particular equation. But in reality, it is not possible to have infinite number of trunks. So in practice, we can have finite number of trunks only. So in such case, we will be dealing with some calls that can be lost. So since we are having finite number of calls, once large number of calls are incoming, we will end up with some calls being lost or some calls will be delayed if we have memory. And the distribution is not going to be Poisson distribution. So when we are having finite number of trunks, if we are having infinite number of trunks, then we can satisfy these equations. But in reality, it is not possible to have infinite number of trunks. So you can have infinite number of trunks also. So when we are dealing with lost calls being lost, we will be dealing with lost call system. If the calls are being delayed, then we will be dealing with queuing system. So next we will deal with lost call system and queuing system in our coming class. Thank you.